Morning. Any questions, concerns? Okay, you can pick up your questions. They are now available. Upstairs by Nicole's office, there is a bookshelf. You can go there and pick your questions up. Okay, any questions on quiz? No? Okay, as I said before, I don't mark your quizzes, assignments, and midterm. So the TAs mark for you. So please be a little more specific and try to be neat, clean, and your handwritings must be legible. Okay. So still, if you are not happy with your marks, just come to me and see. Okay. Eric, yeah, happy with your mark? Because you look upset. Okay, about filters, any questions on filters? So we learned before we learned passband filter. So how did we design a passband filter? We use a unity gain low pass filter and unity gain high pass filter, and after that we use a gain circuit. So omega C2 is generated by low pass filter or high pass filter? Low pass filter. And omega C1 is generated by high pass filter. And this gain, we use it just to increase the gain from unity to whatever we want. For this plot, 20 dB, but it can be any gain. So after that, we use low pass filter, high pass filter, and inverting amplifier. This is our gain circuit, this is our high pass filter, and this one is our low pass filter. So the transfer function is this. So because we assume that this is the broadband filter, so omega C2 is much, much greater than omega C1. So omega C1 plus omega C2 is about equal to omega C2. After rearranging the equation, we get this one for the transfer function. So the cutoff frequency omega C2 is 1 over RLCL. Why RLCL? Because the low pass filter is responsible for creating the higher cutoff frequency, which is omega C2, and omega C1 is 1 over RHCH, and again 1 RH and CH because the high pass filter is responsible for generating the cutoff frequency, which is over here omega C1. Now for band reject filter, again we use the unity gain low pass filter, which has the cutoff frequency of omega C1. Now for the band reject filter, the low pass filter is responsible for producing the lower cutoff frequency omega C1, and we use high pass filter, the unity gain high pass filter, which produces omega C2, the higher cutoff frequency. And after that, we use gain component to get the desired level of gain in the pass bands. So from here, you see omega C1, here this one is low pass filter, the cutoff frequency for low pass filter, and omega C2 is the cutoff frequency for the high pass filter. And after that, we use the gain circuit just to get the desired level of gain. Okay, any questions? So the difference between the band reject filter and pass band filter is, what is the difference? In band pass filter, omega C2 or the higher frequency is produced by low pass filter, and omega C1 is produced by high pass filter. But in band reject filter, omega C1 is produced by low pass filter and omega C2 by high pass filter. So this is one kind of band reject filter. So we have low pass filter in parallel with high pass filter, and after that we have a summing amplifier. So what is the transfer function for this? The transfer function for this circuit. What is the transfer function for this circuit? V out over Vi. So how do you calculate the relation between V out and Vi? The output voltage and the input voltage. What's that? For example, we have this circuit. This one is a low pass filter, and this one is a high pass filter, and this one is a summing amplifier. So how do you calculate the transfer function for this circuit? Try it yourself now and find the transfer function for this circuit. What is the transfer function for the low pass filter? You see over here. if the output voltage, I call it now VOL. So VOL over VI is negative 1 over CLRL over S plus 1 over CLRL. You know how to get this equation, don't you? So this one is for the low pass filter. The transfer function, it means the output voltage, the relation between V out L and VI is this. And how about the high pass filter we have over here? V out H, we call it now V out H, over VI is this. Now you have a summing amplifier. One input is connected to, sorry, this one is connected to this, and this one is ground. Okay, now you have two input voltages. One of them is V out L, another one is V out H, and this one is your output. So what is the relation between the output voltage and input voltages in summing amplifier? Is negative RF over RI multiplied by V out L plus RF over RI multiplied by V out H, this the second input. So V out is minus RFI. This is the common factor for both terms. So minus RFI. So what is V out L? This is V out L. This is V out over VI. So we have this one. And for V out H over VI, we have this equation, this one. So we get this. That's why the transfer function for this circuit is minus RF over RI multiplied by minus omega C1 over S plus omega C1 plus minus S over S plus omega C2. This is the transfer function for this circuit. Any questions on that? How this equation is calculated? Okay, so we have the transfer function, we have the circuit. Again, after that, this is the transfer function. So add, we have one term, two term, get the common denominator from this one and rearrange the equation. We'll get this one. Again, the same thing because we have a broadband filter. Omega C2 is much, much greater than omega C1. And what is omega C1 over here? 1 over RLCL, because this is band reject filter. And how about omega C2? Is 1 over RHCH. Practice example 15.6. Let me go through the example. Design a circuit based on the parallel band reject op-amp filter in the circuit shown here. This is the circuit, we have it, and we have the body plot for this filter. And the question asks us to use 0.5 microfarad capacitors in your design. So this is the circuit. Why we have this kind of circuit? Because the question is about band reject filter. So this is a band reject filter. So for capacitors, two capacitors we have over here, we use 0.5 microfarad. Now we want to calculate the values for RL, RH, RF, and RI. We got over here. So this is the body plot for the above circuit. So calculate the values for RL, RH, and RF, RI. Now you do it yourself, please. Because this is a band reject filter, how many cutoff frequencies do we have? Two cutoff frequencies. The lower cutoff frequency and the higher cutoff frequency. So what is the equation for the lower cutoff frequency? For the lower cutoff frequency?
Isn't it 1 over RLCL?
Yes, because this is a band reject filter and the low pass filter is responsible for generating the lower cutoff frequency because of band reject. So for exam, make sure that your answer is correct, okay? Don't use RH and CH. Use omega C1 equal to 1 over CL RL. But if it was a band pass filter, so omega C1 would be 1 over RHCH. Yes. So you have omega C1. What is omega C1 over here? How much is it? 100 watt radians over second. And how about the omega C2, the higher cutoff frequency? It's 2000. So at least you can calculate RL and RH. What's the value for RL? 0.5 microfarad. This is the value for the capacitor. RL is why aren't you happy today? Because of the quiz or something else? What's going on? Smile, be happy. Have positive vibes. Yeah, I like this class now. Yeah, smile, laugh, it's okay. But don't be upset or sad. Okay, what's the value for RL? 20K ohm. And how about RH? One kilo ohm. 1 kilo ohm? Okay. RL is 20 kilo ohms. Why? Because omega C1 is 1 over RL CL. And what is the value for omega C1? 100 radians over second. And we have the value for CL. So from there, RL is 20 kilo ohms. And how about RH? The same thing, omega C2 is 1 over CHRH. What is the value for omega C2? What is the value for omega C2? 2000. Yes. So RH will be how much? 1K? 1 kilo ohm. Okay. So there is a question over here. Do you see this dash line? So this line means it says that it is 6.54. So what is the maximum value for this filter? What is the gain for this filter? What does the dash line represent to you? What's that? Minus 3 dB, what? What's that? Minus 3 dB. Redden, what?
Minus 3 dB of
Yes, it means it is the magnitude of the transfer function at the cutoff frequencies. So because these two are cutoff frequencies and minus 3 dB, it is 6.54. It is dB. It is in dB. So what is the gain now for this filter? What is the maximum value? So this dash line is 6.54 in dB. So what is the maximum value? Eric, what's the maximum value?
I don't know.
You are confused with the negative 3 dB. So do you remember how we calculate minus 3 dB? Okay, how did we calculate negative 3 dB? How did we calculate it? Okay, do you have a calculator, Eric? So calculate logarithm 1 over square root of 2 and then multiply it by 20. So how much you got? 14. No, log.
Oh.
1 over square root of 2. Then after that, multiply your answer by 20. How much you got? Minus 3.0 something. Yes, that's right. So that's why we say minus 3 dB. So what is that? You calculate it. Just give me the value for log 1 over square root of 2 and after that multiply by 2. How much?
Negative 3.01.
Okay. So why did we do that? Why did we get log of 1 over square root of 2 and then multiply by 20? Why?
Like the magnitude of the transfer function once it's been reduced by 1 over 2, so like the maximum.
Yes. Yeah, that's correct. The magnitude of the transfer function at the cutoff frequencies here, because we have two frequencies, is equal to 1 over square root of 2 multiplied by h max. Do you remember this equation? So it means if this is maximum value, which is really the maximum value, or the gain for the filter, so this one is the maximum value. If this is multiplied by 1 over square root of 2, it will give me the magnitude of the transfer function at cutoff frequencies. So this one is the cutoff frequency. This one is the higher cutoff frequency. So this line is 6.54. So the magnitude of the transfer function at cutoff frequencies is 6.54 dB. So what is the maximum value for this filter or this circuit? If you convert the value to dB, it means the magnitude of the transfer function at cutoff frequency is 3 dB lower than the gain. 3 dB lower than the gain. That's why you have negative 3. Is that clear? Please, everybody. For a second, just listen to me. The magnitude of the transfer function at the cutoff frequency is equal to 1 over square root of 2 multiplied by the maximum value for the transfer function. Is that clear? So if you want to convert it to dB, 1 over square root of 2 is negative 3. Okay? So if we are in dB, the units are in dBs for this one, y-axis, you see over here. Okay? So in dBs means if you have the maximum value over here, this one is the maximum value. 3 dB you go down, 3 dB you go down, you will get the value for the cutoff frequencies. Here, because we have two cutoff frequencies, so 3 dB you go down, this is 3 dB down, which is 6.54. You go over here, the first one is the lower cutoff frequency, and the second one is the higher cutoff frequency. Is that clear? So 3 dB below the maximum value. So what is the maximum value for this one? 9.54. Yes, in dB. So now you convert it to number. How much will be? Why 3 times? Just convert it. Do you know how to convert the value to dB or dB to value?
That's dB already.
Yes. So 9.54 is equal to 20 times log of something. So you calculate that number. What is that?
First you have to divide by the 20 and you take the exponential.
10 to. Do it now. Learn. So you have 9.54, which is the gain or the maximum value in dBs. How do you calculate it to number? So 9.54 is equal to 20 times log something base is 10.
Well, 2.9. No, yeah.
Okay, Omar got 3. How much you got? 1. You got no. Okay, if this is not natural log, this is log. So the base is 10. 3, yes. Rounded off 3, yes, that's correct. So how much you got, Aidan? Yeah, that's right. So this is, what is the gain for this circuit now? What is the gain for this circuit? 3. Yeah. Maximum you got 3? Okay.
What's the value for that? What's the unit?
It is the gain. You have this circuit over here, okay? This is the gain circuit. So do you remember we said K is equal to RF over RI? when we use gain circuit or inverting amplifier. Yes. So that is the value for K. It means RF over R. Okay. So this is the gain. Now we don't have unity gain. Okay. Yes, this way. This one is the unity gain low pass filter, unity gain high pass filter. After that we use gain circuit just to change the gain to the desired level. Okay. So now for this one, 3 is the gain. So over here you see gain stage, K is RF over RI, which is 3. If RI is 1 kilo ohm, from here you can calculate RF, which is 3 kilo ohm. You use the gain to calculate the values for RF or RI. In exam, on quiz or midterm, I will give you the value for RI. Let it be RI 1 kilo ohm. So RF will be 3 kilo ohm. Clear? Yes? Question? What's that? What's that? Where did I say RF is 3? Where? So no, I just showed the final answers. You just assume that this is RF.
Okay.
Yeah. Sorry. Yeah. You assume that you don't have the values. Yes, Maxim.
So I thought when we took the 20 log, we were taking it up the magnitude of the transfer function. So if we went back, didn't we find the transfer function not the gain? Like I'm confused how we got to the gain there.
Okay. For this circuit.
Yeah.
Okay.
Like what we just did. Like I understand how we got 3, but I'm confused how it's the gain.
Okay.
Because I thought it was the magnitude of the transfer function.
Okay, let me explain. Yeah, thank you for the question. So this line, dash line, what does this represent to you again?
That's the magnitude of the transfer function when it's been reduced by 1.
Over square root of 2. But because this one gives us omega C1 and omega C2, for sure we say that 6.54 is the magnitude of the transfer function at cutoff frequencies. Okay, so that is clear in dBs. This is dB. So we know that if we go, this is 3 dB below the maximum value or the gain. So if 6.54, you plus it by 3, plus if it say 6.54 plus 3 will be 9.54. So 9.54 is the value for this one, the maximum in dBs. So you convert 9.54 to a number because in dB, how much you will get? You will get 3. So 3 is the gain. In dBs is 9.54, but in number is 3 because you convert. Let me happen, or you want me to explain one more time?
Well, I thought that would have been aren't we saying that that's the max?
Yeah, that is the max. The
Oh,
maximum value.
I
H
got it
max.
now. I get it.
H max. This is our H max.
Yeah.
Yep, the
Yeah,
maximum. This is the transfer function, and this is the maximum value for our transfer function.
Because when H max is maximum, it's just equal to the gain.
Yes.
Okay.
Yes.
There we go.
Okay, any other questions?
So what's the cutoff frequency given, or
Okay, for this one, you have to understand because this is omega C1, so this one is 100. This is given for this question. And omega C2 is 2000, right? Radians per second.
I wasn't sure how we calculated the cutoff frequency.
Okay. How did you calculate the cutoff frequency for this circuit, or you want?
Like in general.
Okay, 1 over R CL. If you have the values for R and CL, easily you can calculate omega C. Yes. Okay. Do you see this line? What is the value for this line? 6.54. So because this line shows omega C1 and omega C2, the cutoff frequencies, when this y-axis is the magnitude of the transfer function. So this line shows us the magnitude of transfer function at cutoff frequency, at omega C now. So this one is equal to 1 over square root of 2 h max.
I don't think I got the point across in the question. So the 9.4 that we used to in the log calculation, where did that?
Okay, from here, 3 dB.
Yeah.
This is 6.54 plus 3 will be 9.54
From the gain.
from the gain. So this is the maximum value. So you have 9.54 in dB. So is equal to 20 times log.
So we just did the log thing just to verify it.
Just to get in, because the gain is not this equation is not in dBs. This one RF over RI. This is in number, right? So that's why you have to convert it from dB to number. Okay, question? Eric? Yara? Sometimes we need to use higher order of amp filters. Why? For example, if we use cascading identical filters, you see if we use this first order filter, you see this curve. As more filters are added to the cascade, the transition from the pass band to the stop band becomes sharper. So if I use another low pass filter, the second one, I got sharper transition. Again, if I use the third one, this line will be sharper and the fourth one will be more sharp over here. Do you see? So that is the use. Why sometimes we need to use cascading filters. For this example, we use the low pass filter. If we use just one, the first order we call it, this will be the plot. But if we use two cascading low pass filter, we get sharper transition between the pass band and stop band. This one is how many order for this example? If we didn't have, we had just 1, 2, 3. We didn't have these dots. They were all connected. 3. But this one is for n, okay? What is the transfer function for the first one? If we use unity gain and the cutoff frequency is 1 radian over second. The cutoff, the transfer function for the first one will be minus 1 over s plus 1. The second one will be minus 1 over s plus 1, so on and so forth. So the final value will be minus 1 to n divided by s plus 1 to n. Again, we are using unity gain low pass filter, and the cutoff frequency happens at 1 radian over second. Okay, from here, if you want to find the cutoff frequency for cascading filters, this is the final equation. So this one is the cutoff frequency for cascading filters. So if we had just 4 cascading filters, what would be the cutoff frequency? Would you please calculate it for me?
You said 4, correct?
4. What's the cutoff frequency?
I thought 0.435.
Yes, that's right. So square root of fourth root of 2 minus 1 will be 0.4 something. Practice example 15.7. Okay, the last kind of filters, Butterworth filters. Again, a unity gain Butterworth low pass filter has a transfer function whose magnitude is given by this, where n is an integer that denotes the order of the filter. So if we have two cascading filters, it means the order is 2. Over here, if we have 3, it means the order is 3, so on and so forth. So from there, we can calculate the cutoff frequency or the transfer function. So how do we design Butterworth filters? I just show you the proof for this equation. You can go through my notes. If you have questions, you can ask me throughout the tutorials. So the procedure is find the roots of the denominator for this transfer function. Hs multiplied by h minus s is this. You find the roots for this polynomial, 1 plus minus 1 to n multiplied by s to 2n. So make it equal to 0. From here, you can calculate the roots question. Okay, this is the first step. The second step is assign the left half plane roots of hs and the right half plane roots to h minus s. Then combine the terms in the denominator, so you can have now you have designed a Butterworth filter. So let me explain it more through this example. Find the Butterworth transfer function for n2 and n3. So for the first step, n is 2. So we have this transfer function over here, hs multiplied by h minus s. So we have this one. What is the first step? Find the roots of this term or polynomial. So now because n is 2, if n is 2, sorry, you just correct over here, n is 2 is not 0 in my notes. So if n is 2, we have 1 plus minus 1 squared s to 4. So s raised to the power 4 is equal to minus 1. So what is the meaning of minus 1? The magnitude of minus 1 is 1. And how about the angle? How about the angle? 180 degrees. Okay. So minus 1, the magnitude of minus 1 is 1, and the angle is 180 degrees. So I can write it down like this. Get the fourth root from both sides of the equation. you will get this. So S is E to J pi over 4. What's that? Why is it negative 1? Try it. Try it yourself and see why. So this one squared is positive. So S is 1 plus S to 4 is 0. So S4 is minus 4. Or negative 1. Okay, now S is E raised to the power J pi over 4. You draw this unity circle over here. Because this is 4, 360 degrees we have around this circle. If you divide it by 4, what will be the distance between each root? 360 degrees divided by 4, 90 degrees. So what is the first angle? 45 degrees. Why? Because pi over 4 is 45 degrees. So S1 is, the magnitude is 1, the magnitude is 1, and the angle is 45 degrees. You just transfer it to the rectangular representation, and I hope you remember how to do that. Phil, do you remember? From polar representation to rectangular representation? Okay, but you know the procedure. Okay, everybody knows the procedure from polar representation to rectangular representation? Okay. So S2 again, the magnitude is 1, and 45 degrees plus 90 degrees will be 135 degrees. Again, this is the rectangular representation. 135 degrees plus 90 is 225 degrees. This is the polar representation, rectangular representation, and again plus 90 we have 315 degrees. So you have 1, 2, 3, 4 roots. S1, S2, S3, S4. What is the second step? The second step, sign the left half plane roots 2. This is not off. This is 2. 2h of S. So we have 2 roots on the left plane, these 2. What are these 2? This is 45. So this is 1, S2, and S3. S2 and S3 are in the left half plane. So what are the roots for this one? Minus 1 over square root of 2 plus j over square root of 2. So it will be 1 over s plus 1 over square root of 2 minus j over square root of 2 multiplied by this one. This is minus, so we have plus over here. So if you multiply them, if you multiply this one by this, you will get this one. So this is the transfer function for this Butterworth filter. Not happy? Okay, I don't mind if I explain it one more time. Want me to explain one more time? To design Butterworth filters, there are 3 steps. So first step is you have this transfer function and you have this polynomial over here. This one. Find the roots. Okay, find the roots for this polynomial. Because we have n2, this is 2 again, corrected in my notes. We'll get this value for s. So it means we have 4 roots. So divide 360 degrees by 4. How much we get? 90 degrees. It means each root is apart from another root by 90 degrees. And what is the first root? We can start from 45 degrees. Okay. And after 45, add 90 degrees. Yes, Eric?
How did you know to start at 45?
You can start from anywhere else, but because this is pi over 4, pi over 4 is how much?
Well, where did the higher 4 come from?
Okay, that is a good question. Where did it come from? You have s raised to the power 4, which is minus 1. So what is minus 1? The magnitude is 1 and the angle is 180 degrees. So 1e raised to the power j pi. So you have s4 over here, s to 4, and you have this one on the other side of the equation. Get the fourth root from both sides of the equation. So you get s. Fourth root of this one is j pi over 4. Pi over 4 is 45 degrees. So start from 45 degrees and plus 90 degrees to that. You will get the second root. And after that, plus 94 degrees, you get the third one. And plus 90 degrees, you will get fourth one. Yes, Eric. Sorry.
You only start the same equation at the top?
Yes.
It's always that one?
That is it.
Okay, so you just change the end?
No, just the order if for n. Do you see over here? This is the same, just n is different.
Okay.
Yes, Max.
How did you know to add the 90 degrees to it every time?
Because we have 4 roots, so 360 divided by 4, we have 90 degrees. So roots must be apart from each other by 90 degrees.
So like say we have like 7 roots, then we divide by 360 by 7.
We have now n3. Okay. Is that clear? Everybody? Tyler? Okay. Now try, after that you have these 2 roots on the left side, S2 and S3, S2 and S3. So assign over here, assign the left half plane roots to h of s. So we have these two, S2 and S3, we assign them to h of s, so we have the transfer function. That is the transfer function. Okay? How about N3? Try it now. And for N3, N is 3. So the first step is this one. You have this equation, the same equation. Now n is 3. From there, find the roots. Because we use unity gain filters, we always have the magnitude of 1. That's why the circle is unit. The radius of the circle is 1. Okay, we use the same polynomial. And now n is 3. So 1 plus negative 1 raised to the power 3 multiplied by s raised to the power 6, 0. So s raised to the power 6 is 1 now. So what is 1? The magnitude is 1. What is the angle? Angle is 0 degree or 360 degrees. So 1 e raised to the power j 2 pi, and get the sec root from both sides of the equation. Why sec root? Because s is s to the raised to the power 6. So you will get this one, this equation. So from here, s is e to j pi over 3. So what is pi over 3? Pi over 3 is how much? 60 degrees. So how many s's do you have on the circle? 6. So 360 divided by 6 is 60 degrees. So S, the roots must be 60 degrees apart from each other. So you have 3 S's over here in the right hand and 3 S's in the left hand. So if you start from 60, because pi over 3, Eric, because pi over 3 is 60, so you'll get this one. Plus 60, you will get 120 degrees, plus 60, 180 degrees, plus 60, 240 degrees, after that 300 degrees, and then plus 60, 360 degrees, or 0, this one. So you have these 3 S's over here. So what is the last step? Assign the roots which are in the left hand side or in the left half of this circle, these 3, to h of s or hs. So what is the first one? This one. One is this. So plus 1 over 2 minus j square root of 3 over 2. Another one is this, minus 1. So we have s plus 1. And another one is this. So we have plus half plus j multiplied by 3 over 2. If you multiply these 3 terms, you will get this. Sorry, these 2. You multiply this one by this, you will get this. So this is the transfer function for this question. Eric, did you get the same answer? Okay, so is that clear now? So what is the first step? You have this polynomial, you have the value for n, you find s from here, and see over here, because we have 6, so divide 360 degrees by 6. So how much you will get? 60 degrees. It means each root must be 60 degrees apart from another one. Start from pi over 3 at 60 degrees you will get 6 S's, and assign these 3 to the left side, to H of S or Hs. Clear? Yes.
Could you explain how you go from the to the HS equation?
Yes. So we have these 3 in the left half plane. This one, which is this, and S5, which is this one. Okay. S4 is minus 1. It means the root is minus 1. So S plus 1 will give me root minus 1. For this one, S, because we have minus, just send it to other side of the equation. You will get plus 1 over 2 minus J square root of 3 over 2. And for this one, send it to this side of the equation, plus 1 over 2 and plus J square root of 3 over 2. Yes. So if you want to use on the right hand, I told you, just assign it to H of minus or negative S. We are just interested in knowing H S or H minus S. So HS is enough for us. Questions? I think that's enough for today. I don't want to make it more difficult for you. What's your name? Your name? Yes. Justin? Would you please send me an email? Let me think about it, okay? And write your concerns, okay? From Wednesday to Fridays, okay? Okay, just send me an email, okay? Remind me. Okay, any questions? Yes.
Her system is like the same week as the next. So like in November.